All right. In this section, we're going to talk about proving conditional statements or if-then statements. As a quick reminder from our last video, this whole idea of the dreaded row in an if-then statement where the if part is true and the then part is false, that's the only time where the if-then or conditional statement is false. So we're trying to show that that will never happen. That's the idea of proving an if-then statement, is avoiding this dreaded row. And just to see some examples, a lot of our easy examples are going to come with the idea of even and odd numbers. So pause the video now and see if you guys can remind yourselves how to write an even number and an odd number in general. So try and do that. Okay, so hopefully you remembered from previous videos that even numbers, well, what does it mean for a number to be even? It has a factor of 2, so I can write it as 2 times k for some whole number k. And an odd number is going to be like an even number, except one more than it. So it can be written as 2k plus 1, again, for some whole number k. Now, writing for some whole number k will get tiresome after a while. Eventually, we'll come up with some nice notation for that, so we don't have to keep writing these words over and over again. And we'll do that in the next section when we talk about sets. All right. Well, remember, k just has to be a whole number. So maybe you have some other whole numbers that are added or multiplied together, and it'll still be an even number, or an odd number if you can write it as 2k plus 1. Let me show you what I mean. So let's consider the following. 2a plus 4b plus 6. Now, I notice that each of my terms here has a factor of 2. So I can factor that out. So this is the same as 2 times a plus 2b plus 3. And you can check that if I multiply this back, 2 times a is 2a, 2 times b is 4b, 2 times 3 is 6. I get the same thing. But look here. If a and b, let me just tell you, a and b are whole numbers. Since a and b are whole numbers, we have this idea of adding and multiplying whole numbers, and we get another whole number. So this indeed here, this is a whole number. This is like our k. So I can write this as 2 times some whole number, a plus 2b plus 3. Whatever a and b are, we know they're whole numbers. So this a plus 2b plus 3 is a whole number. So I wrote 2a plus 4b plus 6 as 2 times a whole number. Well, that means, since I did that, that means that the original expression, 2a plus 4b plus 6, is even. And similarly, let's do something like this. 4r plus 8 s squared plus 7. Let's look at this expression. And you could say, well, we have the squared here. I'm going to tell you again, sorry, that r and s are whole numbers. So I can write this as something of the form 2 times a whole number plus 1. So let me go ahead and do that. I notice that this guy is just 6 plus 1. And then I can do the same. If I take away that plus 1, I have that same idea as up here, where I have a bunch of factors of 2 in each term. Or I should say 1 factor of 2 in a bunch of terms, which I can take out. So let me go ahead and do that. This is the same thing as 4r plus 8s squared plus 6 plus 1. So if I can write this as a bunch of even things plus 1, well, I can factor out a 2 from each of these even terms. So this is the same as 2 times 2r plus 4s squared plus 3 plus 1. And if you think about it, you're like, oh, what we're squaring now, so I don't know if we're still going to get a whole number. But what does s squared mean? This just means s times s. If s is a whole number, s times s is going to be a whole number. So we're still adding and multiplying whole numbers here. So this, in fact, is indeed another whole number. So this original expression, I won't write it again, but this original expression is odd, since I was able to write it as 2 times a whole number plus 1. So my k in the second example is 2r plus 4s squared plus 3. Remember, the whole idea, all even numbers can be written as 2 times a whole number. Odd numbers can be written as 2 times a whole number plus 1. So since I can do that, I know that the numbers are even and odd respectively. Let's look at one more example. Let's consider 3j. Let's just do something easy. 3j plus 1. Is this even or odd? Well, in fact, this one, you could think, well, maybe I can do something similar. But if you play around with it a little bit, you'll find that, let's say j is a whole number here first. You find that there's no nice way of making it into a number that's always even or always odd. And there's a reason for that. It's because depending on j, our number could be either even or odd. So this, if j was, say, 1, then 3 times j, which is 1 plus 1, is 4, which is even. But if j was 2, then 3 times 2 plus 1 is 7. 6 plus 1 is 7, which is odd. So this expression, 3j plus 1, is neither always even or always odd. So we found some examples for each of them. We can think of them with the word counterexample, and we'll talk about what a counterexample is in the next video in a little more detail. But it's an example that shows something is false. Again, these expressions above, no matter what a and b are, these are always going to be even, since it's 2 times some whole number. It doesn't matter what a and b are, this is still 2 times some whole number. Here, doesn't matter what r and s are. This is 2 times some whole number plus 1. With this expression, it does matter. If, for example, if j was 1, then the expression is even. If j was 2, the expression is odd. So it depends on what j is for this expression to be even or odd. So we can't say either way. So let's look at this first example here. Prove that if n and m are even numbers, then n plus n is even. And let me remind you yet again of the truth table for an if-then statement, because we're going to talk about our first technique, and it's going to be the one that we're going to rely on for most of this course. It's called a direct method of proving. So there's the truth table for P and Q, and then P imply Q is only false when the if part is true and the then part is false. Now, the whole idea is that we want to show that this dreaded row never happens. So, what the direct method is, well, we're going to pretend that P is true. And if P is true, we want to show that we never end up in the dreaded row. So if we never end up in the dreaded row, it must be, well, if P is true, there's no way that Q could be false. So we need that Q must be true as well. So our first method is the direct method. You're going to assume that P is true. And we're going to show that Q must be true. So that's the direct method. I'm going to talk about the other methods just quickly. We won't see them too often. We might a little bit later in the course. But the other ones, well, this one is called the method of the contraposition. And it's kind of a related idea. But again, we want to show that we're never in this row. So that's if P is true and Q is false. So if P is true, we want to show that Q has to be true, that Q can never be false. But we can kind of do it the other way. Well, instead of assuming P is true, we can assume that Q is false and show that P is never true, that P must be false. So the contraposition way is you're going to assume that Q is false. And again, we want to make sure that we're not in that dreaded row, so we can't have that P is true as well. So we assume Q is false, and we show that P must be false. And the third way is called contradiction. And contradiction, this is kind of a fun one. You pretend you're in the dreaded row. So you say, all right, let's let the if part be true and the then part be false. So assume you're in the dreaded row, so P is true and Q is false. And you show that if that's the case, that kind of your mathematical world blows up. So mathematics blows up. Don't worry about contraposition and contradiction too much for now. We'll talk about them a little more later, but I just want you to get into the idea of how we always prove an if-then statement. We want to show that we're never in this dreaded row. So there's kind of three ways to go about it. Assume P is true, show that Q must be true. Because if Q is false, then we'd be in the dreaded row. Okay, the other way is assume Q is false and show that P can't be true. So we're not going to be in the dreaded row, so we need to show that P must be false. That's contraposition. And then contradiction is to pretend you're in the dreaded row and show that mathematics breaks down. Okay, so let's do the direct method. That's the one we're going to focus on, especially for the first bit of the course. This is the important bit. So we're going to assume that the if part is true. So what's our if part here? Our if part is the following. it is that if n and m are even. Okay, so what does that mean? If n is an even number and m is an even number. So we need to be able to write n and m as even numbers. So we'll call this part 1. Maybe I'll number these. This is step 1, is making your assumptions for p. So we want to assume that n and m are even. So we're going to assume n and m are even. So what does that mean? Well, that means we should be able to write n as 2 times some whole number, and we should be able to write m as 2 times some whole number. But be careful. Remember that n and m are probably different even numbers, so you can't use the same variable to express it. So we already used k to be that number you multiply by 2 to get n. So we need a different variable, let's call it L, to be that number you multiply by 2 to get M. So I introduced the symbols K and L, so I better tell you what they are. Where K and L are whole numbers. Okay. So we finished the first part. We assumed that the if part is true. So now let's do the second part. We want to show that the then part is true. So what do we want to show? Let's write that down. To show. We want to show that the sum of n and m is even. So let me highlight that. So that means we should be able to write the sum as 2 times some whole number. Usually it'll involve brackets. You'll have to do a little bit of algebraic manipulation. But we should be able to write n plus m as 2 times some whole number. So we know what we need to show. So let's go ahead and see if we can do it. The nice thing about this, and we talked a little bit about this in a previous video, so let's consider n plus m. We know what our final answer will look like. It's going to look like 2 times some whole number. So we know where we're going. We just have to be a little bit creative to find the steps to get there. Well, let's use our assumptions. We know n is even, so n is 2 times k. And m is even, so m is 2 times l. So I should be able to write, and actually this is just a one-liner, so I can move this up here. I can factor out that 2, and I get 2 times k plus l. And then maybe you'll just tell the reader, remember this is a communication exercise as well, I can say that since k plus l is a whole number, because I'm just adding whole numbers, then n plus m is even. So I showed that if n is even and m is even, that's the if part being true, then I can always write n plus m as 2 times some whole number. I can always do this. Since I can always do this, the q part is always going to be true. I'm never going to have a place where I have 2 even numbers that I add together that don't give me an even number. So I'm done. And there are the steps for all of these direct proofs. Step 1 is you assume the if part is true. For us it was n and m were even numbers, so we write that down. And the second part is we need to show that q must be true. So we use our assumptions to show that, in this case, n plus m can be written as 2 times some whole number. So that's our example here. I'll give you guys one more to do yourselves that's going to be very similar. So try this. Here's a very similar problem. So prove that if n and m are odd numbers this time, then the sum of them, n plus m, is even. So pause the video now, use the example we just did as a guide, see if you can write down the proof of this. The only difference is going to be that n and m are odd numbers instead of even. Alright, so hopefully you guys have something down, and let's see how I would do this. So step 1 is we want to assume the if part is true, so n and m are odd numbers. So let's assume n and m are odd. So what does that mean? That means n I can write as 2 times, I'm not going to use k and l because I always do, so let me use something different, r and s, doesn't really matter. So it's going to be 2 times r plus 1, and m is 2 times s plus 1 for some r and s that are whole numbers. Alright, so we did the first part. The second part, well, we want to show that n plus m is going to be 2 times some whole number, since we want to show that n plus m is always going to be even. So we know that this is going to be a whole number. If we can show that, we're done. So let's consider what we need to show. N plus m. Well, you know, n is 2r plus 1. M is 2s plus 1. And note, I don't really need these brackets here because it's just a bunch of things added together. But I put them in there just to kind of indicate that n goes with 2r plus 1, and m goes with 2s plus 1, just so it's a little bit easier for the reader to follow along. All right, we know what our answer should look like. It should look like 2 times some whole number. So how are we going to do this? Well, let's combine as many like terms as we can, and really the only things we can combine are the 1 and the 1 to get 2. So if we simplify this, we get 2r plus 2s plus 2, and you can see that all of the terms here have a common factor of 2. If we take it out, we get r plus s plus 1. You can check if you multiply back by 2, you get exactly the line above. And hey, I did it, since r plus s plus 1 is a whole number, n plus m is even, and we're done. Again, these are kind of all the same. In fact, the only kind of work there is, the only bit where you have to be clever, is between here and the answer. So everything else is just being able to translate into the language of mathematics. So the first part is just assuming the if part is true. So how can you write that? If you're assuming n and m are odd numbers, you have to remember what an odd number is. It's just 2 times a whole number plus 1. So n is 2r plus 1, m is 2s plus 1. Again, there's no thinking there, it's just writing it down. The second bit, you write down what you need to show. In fact, you don't strictly need this line, but I think it's a good idea just to remind yourself what you're doing. So you know your final answer is going to be 2 times some whole number. That's the form you want to get. So you write down what you need to start with, so n plus m. And then all of the work is here. It's getting n plus m to look in the form that you want it to. So there's a little bit of cleverness you'll have to do. Realizing, hey, in this case, I need the factor of 2. So let me try and add everything together that I can and see if a factor of 2 will just pop out. And hey, it does. So I will take it out. And then this expression here is, of course, even because it's 2 times some whole number. And all of these are the exact same in that respect, where you go through the same steps and kind of the only work is here. Let's look at one more example. Let's do the following. Let's prove that the sum of 5 consecutive numbers has a factor of 5. Now, the first thing that you should be able to notice is that this isn't necessarily an if-then statement. There's no if, there's no then, but we should be able to reword it to mean the same thing. So pause the video now and see if you can reword this. You might have to give some numbers some names, and that's totally fine. So see if you can rewrite this as an if-then statement. Okay, so let's reword it. Something like this I think is good. So rather than saying the sum of 5 consecutive numbers has a factor of 5, maybe you can say if A, B, C, D, and E, say, are consecutive numbers, then the sum of them has a factor of 5. So that's one way of doing it. I think that's probably one of the better ways. So hopefully you guys got something like that. All right. So now we have this in an if-then form. So again, pause the video and see if you can do this proof using the other two as examples. Remember what you want to show. If something has a factor of 5, it's going to look something like this. 5 times some whole number. So that's what you'll want to show. So pause the video now and give it a try. All right, so let's do this. So we want to do the first part. We want to assume that the if part is true. So assume that A, B, C, D, and E are consecutive. And let's say A is the smallest. And it doesn't really matter which one we pick to be the smallest, but let's just do it in alphabetical order, where A is the smallest. Then, well, B, let's do the, B is just going to be the next one, so A plus 1. C is A plus 2. D is A plus 3. And E is A plus 4. So there are 5 consecutive numbers. A plus 1, A plus 2, A plus 3, A plus 4. Okay, so we made our assumption. That's great. We want to show that A plus B plus C plus D plus E, the sum of our 5 consecutive numbers, can be written as 5 times some whole number. That's what it means to have a factor of 5. Remember, even numbers, what does it mean to be even? It means to have a factor of 2. So it's the same idea, except it's 5 instead of 2. All right, so let's consider our expression A plus B plus C plus D plus E. But remember, these are all consecutive, so B is A plus 1, C is A plus 2, D is A plus 3, E is A plus 4. And let's combine our like terms. We have 1, 2, 3, 4, 5 A's. And then we have 1 plus 2 plus 3 plus 4, which is 10. And remember, we want to get this in the form 5 times some whole number. But hey, look here. We have a factor of 5 in all of our terms here, which is great, which means we can take it out. So let's go ahead and do that. We get 5 times A plus 2. And we can say, since A plus 2 is a whole number, we know that the result is true. We know our conditional statement is true. We're never going to be in that situation where the if part is true and the then part is false, where we have 5 consecutive numbers here, and the sum doesn't have a factor of 5. We'll never be in that situation. We're always in the situation where we have 5 consecutive numbers, and the sum has a factor of 5. So there is our next example.